Hi everyone. So previously we've explored the example of drawing samples from something like a truncated Gaussian. So this was our pi of r, versus r, and this turns out to be a pretty difficult distribution to sample from. And we had started off with a proposal distribution, which was, well, I should say it was a normal. And the challenge is that, of course, the normal has a support which exceeds, for example, that of the pi of r. Pi of r is 0, or the particular pi of r, the target distribution we're exploring, has 0 density below 0, and a Gaussian distribution has support everywhere. So it was a little bit of an inefficient sampler because we could end up proposing negative values, and those by default would always get rejected, and the acceptance ratio, pi, evaluated at r proposed would be 0. So that wasn't very good. One option, maybe something we can do that's a little bit better, is to select a proposal distribution which only has positive density. And one option for that is to choose a proposal distribution which is, for example, a gamma distribution with two hyperparameters, alpha and r old over alpha, as our shape and as our scale parameter. In this particular case here, we have some dependency on r old, and so we will start exploring things in proportion to r old, or things in a way that depends on r old, but the advantage again is that if, now placing the 0 here, my truncated Gaussian looks something like this, maybe my gamma looks something like this, and I never end up proposing negative values which result in 0 acceptance and therefore improve the efficiency of my Metropolis-Hastings sampler. Now, we've talked about sampling very general targets, but in the previous chapter we had explored sort of posterior distributions. So the question is, can we sample? So using MCMC or Metropolis-Hastings samplers, which are a type of MCMC, for posterior distributions. And the answer is, of course, yes. We still start off with some R naught. We still have some kind of proposal distribution. And yet we have a target. Our target may be a little bit different. It may be sort of the theta 1 to k given, I should, in the notation here, I should call it the r 1 to k given my parameters. But I still have a target distribution. The only difference is that my target distribution is my proposal distribution. So let's go ahead and sort of explicitly write down what the acceptance ratio would be here. We have an A of r old, or I should say an A of r proposed, given r old, and that will be the ratio of w 1 to n, r proposed, divided by p of w 1 to n, r old, multiplied by p of r proposed divided by p of r old. So that's the ratio of likelihoods. This is the ratio of priors. What about the evidence, the p of w? Well, the ratio of the evidence is 1. It doesn't even appear because it simply cancels out. It doesn't depend on r proposed. And then finally we have the ratio of our two proposal distributions, r proposed, or q of r old, given r proposed, and r proposed, given r old. And this is really it. Once we have a proposal distribution, once we have a proposal distribution, we can construct its ratios. And the target distribution, instead of being just a general pi of r, is the posterior, which is the probability of r given my w1 to n, and that's obtained by taking the ratio of my likelihoods and my priors. Now, there is one technical challenge involved in writing down an acceptance ratio for posterior distributions. And that's the fact that likelihoods, if we have IID data, for example, are the product of n different distributions. And in fact, even if we don't have IID data, we have Markov data or something like that, it's still the product of a very large number of distributions. So the acceptance ratio actually can be extremely small. And depending on what the ratio of this versus this is, it can either numerically overflow or numerically underflow very rapidly, as these numbers are individually, the numerator and the denominator can be extremely small. So typically we don't work with acceptance ratios, we work with log acceptance ratios if we're trying to draw samples from a posterior. So we're going to define an L, R old, R proposed, and that's going to be the log of P of W 1 to n, R proposed, divided by P of W 1 to n, R old, plus the log, I guess here I can simply say the ratio of priors, plus the log of the ratio of Q's that I don't need to write down again. And this log itself, close bracket, I can decompose as log P of W 1 to n R proposed minus log P of W 1 to n R old plus, and then again I have the log of R proposed, that's my prior, minus the log of P R old plus, the log of Q minus log Q. And in this particular case, it would be Q of R proposed, R old with R proposed here, R old there. Okay, so while this probability can be extremely small, the log of it is not going to be an incredibly small number. So for example, if P is 10 to the minus 56, then the log of that is just negative 56. So it's not too bad. But the thing is that I now have to adjust, for technical reasons, all of my Metropolis-Hastings algorithm, or I have to adapt it slightly to accommodate the fact that I'm now working with a log acceptance criterion, not an acceptance criterion. So what do? Well, I simply say that if log of U is less than or equal to L, R old, R proposed, then accept, and R new is equal to R proposed. So just as I did before, I still draw my U from a uniform random number between 0 and 1, except I now take its log and I compare to the log of my acceptance ratio. And my acceptance ratio, again, I just have to be careful. It's now going to be the sum and the difference of 6 terms, just like I wrote in the previous slide. Now, if log U is greater than R old, R proposed, then we know that we have to reject, and simply R new is equal to R old, just as we had before. So let's consider an example of this, sort of an example of sampling from a posterior target distribution. So here is Metropolis-Hastings, again for my so-called conjugate normal gamma model. And just as before, we have a prior on the precision that has 2 hyperparameters, the scale parameter and the shape parameter. We have a prior, or a conditional prior, on the mean that has, again, 2 hyperparameters. So the mean given tau. And finally, we have the likelihood, just as we had written before, that's a normal distribution, mu, and 1 over tau. We're going to define a Q at this point, whoops, mu old, mu old, tau old, of mu proposed, tau proposed. So we're going to propose two things at once. We're going to propose a change in mu and a change in tau. And that's going to be a normal distribution, which will depend on two variables. Those two variables are going to be the, well, mu proposed, tau proposed. There's going to be a mean associated to this distribution. That's going to be mu old, tau old. And then there's going to be a variance, and I can choose what I want for my variance. I'm going to choose a diagonal covariance matrix with some variance for the mean and some variance for the precision, tau. I don't have to choose the same for each one of them. Okay, so how's my Metropolis Hastings going to work? Well, I need to be a little bit careful. I'm going to start off with some R0. Now I have to be a little bit careful because my R0 at this point is a vector. It's two-dimensional. So I start off with an initial condition, initial guess for mu naught and tau naught. Subsequently, what do I do? Well, I have an acceptance ratio. That acceptance ratio, I'm going to be working with a log of an acceptance ratio. So that's going to be the log of the ratio of likelihoods multiplied by the ratio of priors multiplied by the ratio of Qs. Now, the good news is that the Q is symmetric in terms of my mu's. So the good news is that it will not appear in my log acceptance ratio. It'll cancel out. So this is more of a, Metropolis, if I want to be technically correct, rather than a Metropolis Hastings, because my proposal distributions, again, are symmetric. So let's go ahead and write down what the log acceptance criterion will be. That'll be mu old, tau old, mu proposed, tau proposed. And I need to be a little bit careful here, so it's going to be a little complicated. So it's going to be 1/2 sum over n from 1 to n, tau old, mu old minus wn squared minus tau proposed, mu proposed minus wn squared, close bracket, plus n plus 2 alpha minus 1 over 2 log tau proposed over tau old, plus psi naught over 2. And I'll explain all of these terms in just 1 second. Tau old, mu old minus xi squared minus tau proposed, mu propose minus xi squared, close bracket, plus beta tau old minus tau proposed. And all this is going to be valid for tau proposed greater than 0. And for tau proposed less than or equal to 0, then the log, so I have two conditions, then the log of the acceptance ratio is going to be equal to -infinity. Why? Well, if I propose a precision, or equivalently the inverse variance, which is negative, variance can't be negative, then the target probability is 0. Then the log of the target probability, therefore, is -infinity. So that's what I have. And what if I propose a tau what if I propose a tau exactly, which is greater than 0? Well, then I'm going to get something, and that something is going to be the log of the ratio of the likelihoods multiplied by the ratio of the priors. I don't have the ratio of the proposals again because those cancel out. And what about the ratio of the priors? Well, I have two of them. I have p of mu given tau multiplied by p of tau. So the log of the likelihood is this term. The log of the priors are these three terms here, right? So we just have to be a little bit careful, but in the end, this is what we get. So assuming that we coded up well, then we can start sampling, proposing joint samples for mu and tau. So how is all this going to work? Well, now it's a sort of a joint probability between mu and tau, and that joint distribution, that joint target, in general is going to be quite complicated. So I make some proposal, or I should say I start off with some initial condition. We'll call that tau naught, mu naught. And then I make some proposal, and if I accept it, I move. If I reject it, then my R nu is my R old. And then in principle, I keep moving until ideally I kind of start mostly exploring samples in the region of highest density. And maybe this is what my sort of my topographic map of my target distribution looks like. Right? So I'm making sort of these proposals in two-dimensional space. So here's an example, again, just to summarize, of how we can draw samples from posterior distributions. We just need to be careful, as I said, not to induce any numerical over or underflow in our acceptance ratio. But it does raise sort of, again, these interesting questions pertaining to what do I need to be mindful of, or what do I need to be careful about when I'm drawing samples, when I'm developing proposal distributions. So, choice of proposal distributions. Let's suppose that my target, pi of r, is 1/3 plus 1/3 plus 1/3 of the sum of three normal distributions. This will be sort of, again, r. And the mean of the first normal is at -1, 0. The mean of the second normal is at +1, 0. And the mean of the third normal is at 0, +1. And maybe the variance is the covariance matrix is diagonal and is the same for all three. So if I were to plot sort of the topographic map of this two-dimensional target distribution, one normal is centered at -1, 0, the other one is at +1, 0, and the other one is at 0, +1. And the variance is sort of 0.5, and these guys are all sort of, either 2 or square root 2 away from one another. So these Gaussians won't really overlap. And this is kind of what my target distribution looks like. Interesting. Suppose I did not know how to draw samples from this Gaussian analytically, and I used Metropolis Hastings. But before I do that, actually, let's ask, can I draw samples from this Gaussian analytically? Absolutely. I would use something like ancestral sampling. So first I would decide which one of these three Gaussians I'm going to sample from by flipping sort of a three-sided coin, a three-sided sort of, or three options in a categorical distribution. And once I do that, then I draw the samples from the normal distribution. So yes, I can absolutely draw analytical samples from this target distribution. The question is, what if I used Metropolis Hastings sort of as a demonstrative example? And let's suppose that my proposal distribution is again a two-dimensional normal for x proposed, y proposed as my variables with some mean x old, y old, and some covariance, let's make it up, 0.3 squared. Well, let's call it something even more general. Let's call it lambda squared. Now for this particular example, something very interesting is going to happen, because my target distribution is sort of 3 separate modes which are kind of not crosstalking, not independent. So again, this is my target distribution. And again, it's a topographical map, so this is x if you want, or x, and this is y. And my pi is sort of the topography here. Suppose that I start off with some r0 here, right? This is my r0, which is x0, y0 in 2 dimension. And let's suppose that my lambda isn't too large and I start exploring. Then what? If my lambda is very small, then I keep exploring here. Every time I try to go to these regions of very low density to try to jump from one mode to another, I get killed. My acceptance ratio, again, in this region here, my pi of r proposed is extremely small. So the probability of drawing a uniform random number, which is smaller than this, is very small. So what happens is that the acceptance essentially goes to 0. So if I were to collect a very large number of samples, and I were to ask what does my target distribution look like, it's going to look like this, because I won't have discovered the other modes. Now, similarly, what if I choose a huge lambda? Then if I choose a huge lambda, I start here, I keep on proposing things, they keep on getting rejected because I'm proposing here and there and there and there. Then in the end, the only thing I've done is sort of stayed at the mode where I was. Now I may by chance happen to draw a sample which happens to fall maybe at the end, the tail of the other mode. But even then I'll keep proposing stuff which is all over the place, so that's I'm pretty much going to stay here because the probability, again, the pi of r proposed out here, or out anywhere is essentially 0. So that's not going to look very good either. So we should start thinking, what is an ideal lambda? What is an ideal variance for our proposal distribution? And perhaps a good variance for the proposal distribution is something which is kind of on par with sort of the distance, roughly speaking, between these different peaks, and may also sort of take into consideration the fact that these peaks have some breadth. Now that of course requires us knowing something about the physics or the chemistry that resulted in the target distribution that we have. Right, so generally speaking, that's going to be difficult to determine if our posterior has multiple peaks and where those peaks are located and how we should choose the variance of our proposal distribution to give ourselves the opportunity to explore this. We can do sophisticated things like alternate between different kinds of proposal distributions or have proposal distributions which are mixtures of Gaussians with small variance and Gaussians with large variances. But in general, this will require some sort of thought. So all this simply to say that it's difficult to sort of select the appropriate proposal distributions. We can add one additional sort of thought and talk about so-called additive random walk samplers. This is to sort of distinguish these from things called multiplicative random walk samplers, which we won't be talking about in too much detail here. We've already explored one type of additive random walk sampler, and that's sort of the Gaussian proposal distribution. This is where r proposed is equal to r old plus some perturbation. And typically speaking, we had drawn this perturbation ourselves from a normal distribution with mean 0 and variance lambda squared. So in other words, lambda was the standard deviation. Equivalently, we could have said that r proposed divided by lambda is drawn from a normal distribution with mean 0 and variance 1. And the lambda basically becomes a tunable parameter that we have in order to be able to sort of dictate the volume of the region we explore around r old. So that was an interesting choice of random walk sampler, but there's other choices, and I can give two more. One of them is the uniform random walk sampler. We don't have to choose Gaussian. We can, for example, choose a uniform distribution, which is centered at our R-old with a volume or a size of lambda. And so the uniform here will be drawing anywhere from -1 to 1. We cannot do 0 to 1 because that would imply that we're only going in one particular direction, right? So we have to be sort of centered around R-old. You have to sort of maintain a stationary density. But this is another possible option. A third option is one that we're not going to explore very often, but sometimes this is used in the literature. And that's a so-called student T distribution that has some hyperparameter nu, another kind of distribution which can also be used as additive walk sampler. So again, we're not forced to use normal. We've explored normal quite a few times and sort of defined the volume of the region around R-old based on some lambda, but in practice we can use uniform or we can use other sort of more exotic distributions if we choose to. So this kind of summarizes, broadly speaking, the considerations for Metropolis Hastings samplers. And we've said that Metropolis Hastings samplers can be used for unidimensional distributions, but also multivariate distributions. The example we just looked at was one where we proposed a mean and a precision simultaneously by having a two-dimensional normal as our proposal distribution. But in practice, at least when it comes to high-dimensional distributions, there is another choice which is oftentimes used, and that's the Gibbs sampler. If you can use the Gibbs sampler, it becomes extremely convenient, and oftentimes we can sort of try to speed up individual steps by leveraging sort of Gibbs sampling technology. So this is sort of going to be the focus for the next portion, the next video, and like I said, it's primarily or exclusively used for multidimensional distributions. Thank you.